Tom Richard is a professor of agriculture and biological engineering and the director of Penn State's Institute for Energy and Environment, where he coordinates a network of almost 500 faculty engaged in innovative, interdisciplinary research and education on fossil and renewable energy, energy efficiency, water, climate, ecosystems, and environmental health. His research and teaching focus on applications of fundamental engineering science to microbial and agricultural systems, developing market-based strategies for a more sustainable agriculture and emerging bio-based economy. Dr. Richard currently directs the Northeast Regional Sun Grant Center for the USDA, serves on the Agricultural Sciences Committee of the U.S. EPA Science Advisory Board, and is the Deputy Technical Director for the Department of Energy's National Risk Assessment Partnership for Geologic Carbon Sequestration. Tom is also the author or co-author of over 150 research and technical publications, a fellow of ASABE, and a fellow and past president of the Institute of Biological Engineering. He has a Bachelor of Science from the University of California at Berkeley and an MS and PhD degrees from Cornell University. And at this time, I want to turn the mic over to Tom Richard. Thanks, Tom.
Thank you, Mark, and thanks to all the members of the GreenGov Council and guests that are going to be listening today, and to the Sustainability Institute for helping to organize the invitation. So I'm going to be talking today about carbon emission drawdown and the very important, but I think underappreciated need to start preparing for not just a zero emission world, but a negative emission world. As most of you know, we've already got too much CO2 in the atmosphere. The effects of climate change are being felt today, and it's going to get worse before it gets better. But in order for it to get better, we can't just look at zero emissions as our target, but we have to actually look at negative emissions. And there are a number of ways to do that. And many of them can be quite operational here in Pennsylvania. And I wanted to provide a framework for that today, get a little bit of a discussion going, but also invite further conversations down the road. The term drawdown, many of you will have heard popularized over the last few years by Project Drawdown, which is an effort that has grown to a global analysis of what are the different portfolio of solutions that can address climate change from a perspective of solving it, not just making it less worse. So, and Paul Hawken, who many of you know is sort of one of the pioneers in eco-entrepreneurship and policy, including writing a book, Natural Capitalism, with Amory Lovins many years ago, and several other really signature publications, was one of the founders of this group, and it's done detailed analysis of over 80 different solutions, which are outlined on this slide. And I've highlighted in green and red a few of them that touch on topics we'll mention today. The green ones are in a category that I'll call natural solutions for the most part. But in the upper left, there are also some technical solutions. All of them rely on photosynthesis, and all of them offer opportunities to make things better. And then the red highlights are solutions that, again, offer strategies to reduce emissions, but in that case, more by reducing current emissions from rice cultivation, often in the form of methane and nitrous oxide, from farmland restoration, from cook stoves, which are not currently clean in much of the world, and a plant-rich diet in contrast to meat-rich diet, which livestock systems are fairly heavy emitters from our agricultural systems. But I did also want to emphasize how many of these solutions actually rely on plants and photosynthesis. And when we think about drawdown as the point in time when atmospheric CO2 concentrations begin to decrease, that means we're taking CO2 out of the air. And photosynthesis is a very powerful way to do that. It's been doing it for about 3.5 billion years. It actually gave us the relatively hospitable atmosphere that we have today. And it continues to do that at a fairly substantial level every year. In fact, if some of you may be familiar with the Keeling curve, which is the atmospheric CO2 concentration measured typically, primarily at Mauna Loa volcano in Hawaii, which has been going up for, well, many, many decades, but it goes up in a sawtooth fashion, and the downward slopes of that sawtooth are from plants and photosynthesis in the northern hemisphere, taking CO2 out of the atmosphere at a very measurable and very significant level. A few definitions. First of all, and Mark mentioned carbon sequestration and my work on that topic with the DOE. That term isn't very familiar to a lot of people, but it means storage. So how do we get carbon into a place where it will stay? And in the case of geologic carbon storage, that needs to be for at least 100 years. And there are a number of different geologic formations in which we're quite confident that can occur. There's also what's sometimes called terrestrial sequestration, storing that carbon near the surface, oftentimes in living plant material like the tree trunks and biomass of a forest, but also in soils and in sediments. And then there are also some more technical strategies, such as making materials out of photosynthetic carbon. And actually, people have been doing that for quite a long time, wood being one of our primary early building materials. But there are also newer approaches, which include mass timber construction, bioplastics, and other biomaterials. And I'll come back to that at the end. A couple of acronyms that you may hear, CCS, carbon capture, utilization, and storage, where the capture part could be by photosynthesis or it could be by other means. The utilization would be giving it a purpose that might have a market, like mass timber or bioplastics, and storage being typically the long-term residence of that carbon, which either could be in that marketed material or it could be in a less valuable but still important place like geology or soils or trees. And then BECCS is bioenergy carbon capture and storage, and that could include utilization, but isn't usually abbreviated that way. And the biomass energy really is meant to emphasize that in that kind of energy system, that CO2 is often a byproduct or co-product that can be captured and stored, and that when you do that, unlike fossil carbon capture and storage, which can drive a fossil energy system close to zero emissions, in a biomass energy system, that carbon capture and storage can drive the system into negative emissions territory, which, as I mentioned earlier, is a goal that we need to be looking at very carefully. This idea of negative emissions is not particularly new to the climate researchers and those who've been projecting future climates, and also the potential solutions to that have been considering negative emissions to be a substantial part of our future portfolio. This illustration from 2016 shows projections of the positive emissions in the sort of darker orange color, and then a negative emissions that starts in about 2030 and goes below the zero line, so that the net emissions in the heavy black line can actually drop to the point where in 2070 we hit zero and then start to get into net negative emissions territory. This is a projection to try to hold us to a 2 degree Celsius warming scenario. Unfortunately, we're not hitting the early stage of that trajectory very accurately, even with the Paris Agreement pledges. So we need to do something on this scale, and the scale is substantial. If you look at that 2070 intercept, where that black line hits zero, that means that the negative emissions industry has to be as big as the remaining fossil fuel positive emissions industry, which is substantial. And we're talking about growing that industry from really nothing today into a very substantial sector in just a few decades. This is a summary that Sabine Fuss at the Mercator Institute in Europe has put together on a wide range of negative emissions technologies. And I'm going to focus on the two that are outlined in green and blue over to the left. The green being a series of what are called natural solutions, really depending on photosynthesis and plant material, full stop, to make those things work, but integrated in some places to our agricultural systems. And then in the blue, bringing in some of the agricultural focus that I'll talk about more when I talk about renewable natural gas as one bioenergy strategy that can give us negative emissions. I did want to quickly mention, though, that there are other solutions out there, some of which depend on chemical reactions that can be done at a geologic scale, and also direct air capture, which is sort of in the middle, just to the right of the blue box, which requires essentially artificial photosynthesis to capture the carbon dioxide in the atmosphere and then concentrate it into a fashion that can be either geologically stored or utilized. And to give you a kind of a schematic of that dilute atmosphere carbon storage, this separation process that's in the middle right is basically a catalytic reaction to take the very dilute CO2 in the atmosphere, more concentrated today than it was 100 years ago, but still only on the order of 400 parts per million, which is 3 decimal points below zero, and concentrate that up to 95, 98, 99% CO2, at which point it can be injected into the ground, either into a permanent storage, or actually it's being injected into the ground right now through something that's called enhanced oil recovery, which is a way to get more fossil fuel out of the ground by pushing CO2 in and pressurizing those formations to squeeze out a little bit more oil or natural gas. Unfortunately, that's not really a negative emission strategy because it's enabling additional fossil fuel use. But it does demonstrate that the technology for putting large quantities of CO2 in the ground can be done safely and at scale. This is a hypothetical direct air capture system. Of course, to really get negative emissions, this has to be run on renewable energy. So all those fans would be backed up by solar or wind or some other renewable energy system. This technology has been proven at the lab, and there are a number of companies that are exploring it. But the estimates are that it's several $100s and maybe $500 or $600 per ton at the current technology and costs. The natural solutions relying on plants can be done quite a bit more cost effectively. But it's important to know how they can work and what their limitations are. And this is just a graph of how much carbon can be stored or is typically stored in different types of ecosystems. And it's separated into the below ground carbon soil in contrast to the above ground carbon, which you can see in forests, particularly temperate forests like we have in Pennsylvania, and tropical forests, which we've been very concerned about because of deforestation of the Amazon and parts of Africa and Indonesia, et cetera. There's a lot of carbon in trees above ground, and in those forest environments, it's about a 50-50 split or more. But it's also important to note that in our grassland systems and our agricultural systems, that almost all the carbon storage is below ground in soil. And so the carbon that's above ground is typically harvested every year, or if not harvested, it will decay and go back to the atmosphere. There have been some really good ecologists that have looked at this natural solution set and made estimates for the global carbon storage potential from these solutions. And you can see it illustrated here. And there's some uncertainty about what's possible and what's cost effective. But you can see that at the top where the bars are much longer, it's primarily about forest reforestation, avoided forest conversion, better forest management in plantations or natural forests, fire management, etc. The ag and grasslands are a bit smaller, but there are some really big targets there, including biochar, which we could talk about a little bit later, but also agroforestry, better nutrient management, because there are some significant emissions from conventional fertilizer management, better management of grazing systems and cropping systems, etc. And then it's also important to notice that wetlands are a really big player here as well, along coastlines and peat as a place to potentially store a lot of carbon. When we look at the overall carbon budgets that are projected to be what we need to stay within in order to make that 2-degree warming scenario work, it's on the order of 400 gigatons of CO2. And that's interesting because that's really quite similar to the amount of carbon and CO2 equivalents that we've lost from agricultural soils over the last few hundred years. So it is the case that really ramping up our soil storage and our agricultural systems so that they put a lot more carbon into the soil is a very good idea. And there are some ways that we can do that, many ways that we can do that and still maintain high levels of agricultural productivity, and in fact even greater levels of agricultural productivity over time, because rich organic soils are more productive. They're also much more resilient to stresses, including both drought stress, which we're seeing more of in the Northeast, but also flood stress, which I think we all realize we're seeing a lot more of in the Northeast already as a result of climate change. I want to switch gears a little bit now to the technical solutions and note that this idea of carbon capture and storage is really something that's been primarily demonstrated and developed with the fossil fuel energy system in mind. Here we have a power plant that might be fed coal or natural gas. That CO2 normally gets emitted, but that flue gas can be captured by the same kinds of technology that were discussed for dilute air capture, although there's a really big thermodynamic advantage here, because rather than coming out at 400 parts per million, they're coming out, that CO2 is coming out of a flue stack at something on the order of 10% CO2. And that's a lot easier to separate, although it's still difficult. And the energy required and the parasitic load on the power plant is likely to be on the order of 10 or maybe even 20% of the energy required to capture and concentrate that CO2. The same strategy can be done for a biomass energy system, but here, and I've added some complications, that CO2 can go into the soil during the biological uptake of CO2 during crop production. It can also be captured from the flue gas if that bioenergy was a combustion plant. But I wanted to note that the biogas, or renewable natural gas, that I'll talk about a little bit more later, is a much more concentrated form of CO2, which then means it's much easier to bring up to 99 or 98% CO2 for storage. Biogas is about 60% methane, which is the same element in natural gas, same molecule, and about 40% CO2. So it's 4 times as concentrated as flue gas. And I'll also mention that an ethanol facility like the corn ethanol facility in Clearfield, Pennsylvania, puts out 100% CO2 as a byproduct from that ethanol fermentation. So then that CO2 can be captured through a separation process and then used for electricity. It also can be used as renewable natural gas for natural gas vehicles and transportation. and it can be used as a chemical feedstock. And I think we're all aware that the natural gas industry is looking at all those things for fossil natural gas. Renewable natural gas can substitute in directly, and in fact, the same natural gas grid can be used to move it to those different markets. And it also will generate a CO2 stream that separation process can then use that highly concentrated CO2 for producing other kinds of chemicals and materials, or for geologic storage. We've done some analysis of natural ecosystems and these bioenergy optimized ecosystems, and done that in various areas of the United States, including our region. And the natural systems are really good, and they're very low cost. But illustrated on the left here in B is a typical forest ecosystem, and the degree of carbon dioxide capture that's possible there is on the order of 10 or 15 tons per hectare per year, so about half of that, 7 or 8 per acre per year. And that goes up to over 50 metric tons per hectare per year, or about 25 or 30 tons per acre per year, if we put together one of these energy systems that is both substituting for fossil fuel emissions for our current transportation needs and sequestering a lot of the CO2. So it's a really strong multiplier on a per acre basis. Now that CO2 would be generated in very large quantities, and it would have to go someplace. This is a map of the geologic formations across the U.S. that are considered to be most promising for CO2. And when we add those up, it looks like they could capture all the U.S. emissions that we have today in existing oil and gas fields. That would provide about 35 years of our current emission storage. And if we look at the deep saline aquifers, which are actually here in Pennsylvania, down below the Marcellus and Utica shales, there's over 400 years of storage capacity potential. There are some incentives that have been put in place for doing that kind of geologic storage. They're available both at the federal level and even higher subsidies from California if that CO2 storage is associated with a transportation fuel sold in California. And those costs range from about $50 a ton today. The subsidies range from about $50 a ton today for across the U.S. up to over $200 a ton when you add in the California subsidy, which is good. But if you look at the carbon capture costs for biomass combustion, it would be a typical power plant like we have several of in Pennsylvania, it won't quite pay for that price. However, if you look at a more concentrated CO2 byproduct, such as in an ethanol plant or a biogas plant, then that additional cost of storing that already captured CO2 is quite low relative to the subsidies available, just on the order of about $20 or $21 per ton. There's been some work done nationally to try to estimate what's possible. This is just looking at corn ethanol facilities, and one of the things that one quickly realizes is that a lot of the corn ethanol facilities are in an area of the Midwest, Iowa and Minnesota, the eastern Dakotas, where there really isn't the right kind of geology. And so significant pipeline construction would be required to move that CO2 to the right geology. But if you look at over at Pennsylvania, most of our state actually does have the right type of geology. And in fact, that corn ethanol plant that I mentioned in Clearfield is right over the right kind of geology, and was one of the relatively few plants that this analysis indicated could start doing geologic storage right away. There are alternatives to pipeline, and particularly for smaller generators, and we're very interested in looking at agricultural biogas production, particularly at livestock farms. Those can be put in place with trucks that can haul the CO2 at short distances relatively cost effectively. And that opens up the door for this renewable natural gas that I mentioned earlier, which is a natural process. Anaerobic digestion does occur in all kinds of organic waste materials. As soon as you exclude oxygen, the microbes go to work, and they produce this mixture of about 60% methane and 40% CO2. And then, as mentioned, that can reduce greenhouse gas emissions in several different ways. It's as clean burning as fossil natural gas, but renewable. So the CO2 emissions are essentially real time recaptured by the plant photosynthesis. But you do have to be very careful that you don't release that methane, and that takes a careful construction process and tight fittings on any of the gas transmission lines. In agricultural systems, it actually does also provide the benefit of reducing methane emissions from our conventional manure management systems, and that's actually bundled into the carbon intensity scores that California's done for dairy manure digestion, where their analysis indicates that there's actually a 5 times multiplier of the carbon benefit over and above the transportation reduced emissions that we normally think of as a substitute for renewable fuel. And the carbon dioxide capture and storage is also substantial, essentially doubling that transportation emission benefit from getting a bio-based fuel into transportation instead of a fossil fuel. This is an illustration of the growth in renewable natural gas that's occurred in the 5 years since the EPA started allowing renewable natural gas to count towards the transportation credits. Most of this growth has been in landfills thus far, and that includes several landfills in Pennsylvania. And it's grown quite a bit faster than the cellulosic ethanol liquid fuel growth over the same time period. We've been doing some analysis to look at what those resources look like in Pennsylvania and where they're located. And the potential here is quite substantial. Over 4 billion cubic meters, or about 4 billion cubic meters of natural gas that could be produced. About a quarter of that from landfills, about a quarter of it from manure, and about half of it from crops. The wastewater treatment plants are not trivial, but a relatively small sliver of that overall pie. And I will note, and again, I'd be happy to follow up, but a lot of that crop production would be on marginal land, economically marginal land that we've been identifying through detailed geospatial information system analysis of Pennsylvania farmland, where we're finding pockets of farmland on actually many, many fields where either because of poor soils or proximity to a stream that's flooding, farmers are not getting a very decent profit. In fact, many times getting a loss over a long-term average on that land. We've done that analysis for every county. Again, I won't go into the details, but there's obviously some counties where there's a lot more potential, and the resources are different in different parts of the state. They do overlap pretty well with the geological opportunities, although in the southeast, particularly Lancaster, York counties, Chester County, the geology is not expected to be as good, and we would either need virtual pipelines with trucks or actual pipelines to move the CO2 to the appropriate location. Just getting close to wrapping up, but I wanted to mention that another great place to store carbon is in biomaterials, of which wood is the most common, and a very important industry in Pennsylvania. Roughly a $6 billion industry every year today, and the wood products industry here could expand. Our forests are growing nicely, and there's the potential for harvest more if we could find ways to cost effectively get that forest material into products in a sustainable fashion. And when we look at the overall biomass sector, those forest products opportunities are a very important part of what Pennsylvania's potential would be. And just to give you a sense of the magnitude, if we look at using that wood in construction instead of concrete and steel, both of which have very heavy carbon footprints, because carbon is not just required, or CO2 emissions are not just required in the production from the energy required to make concrete and steel, but also in the chemical reactions to turn limestone into cement and iron ore into high carbon steel. And those multipliers are on the order of 2 kilograms of carbon saved per kilogram of carbon in the wood. So it's a really nice multiplier. So I wanted to stop here by just reminding us of a few key takeaways to tee up the discussion. One is that we do really need negative carbon solutions. That zero carbon emissions is a great goal, but it's one that we have to meet soon and then exceed if we're going to get back to a stable, compatible climate. The photosynthesis is a low-cost way to get that CO2 captured and concentrated and into plant material. That plant biomass can be either a natural solution on its own in combination with sequestration in soil, but also can be a feedstock into various technical solutions, of which I've spent time mostly on biomass energy, but also don't want to ignore biomaterials. But the natural solutions can both be low cost and regenerative in terms of improving our forests and agriculture, making them more resilient for the future as well as the present. That the technical solutions scale and can actually be an economic driver, but they do need markets, and they will need some support to scale initially, as well as some regulatory and policy support. And finally, that there are a number of hybrid natural and technical solutions where we can actually build better and more sustainable agricultural and forestry systems, as well as economic opportunities for a bioeconomy that I think can provide us with a win-win for negative carbon solutions, for sustainable landscapes, and for economic development across Pennsylvania. I want to thank the many students that have worked on this effort, both at Penn State, and we've had a great program for the last few years, and we're hoping to extend, called Drawdown Scholars, where we've brought students to Penn State, and this year it was done virtually, but from around the country and really around the world, to work on climate solutions with our faculty and students. And also the sponsors that have helped support the analysis, that some of which I've just described. So I think I can wrap up there, and I do have one more slide that's the schedule, but I think we might want to do questions first. Is that right, Mark?
Yep. Yeah, thanks, Tom. This was a great presentation that you distilled down into all these technical details into a short, brief summary, which is fantastic. And you do have a lot of questions, or at least a few questions that we can get through. At this time, I'm going to stop the recording, and you can, if folks want to ask questions directly, you can do that.